All right. So one of my students, he's helping us to admit the new people join us. Good morning, everyone. So my name is Wei Song Shi, the Associate Dean for Research and Graduate Studies at the College of Engineering, Wayne State University. So welcome to the 5th version of our Global Engineering Education Jessup seminar series. So before I introduce today's speaker, I just want to give you a little bit background of this speaker series. So at the College of Engineering in Wayne State, so global education is one of our key pillars. So we have putting a lot of effort here. It's a two-way kind of global education. We have the partner universities. You have joined the program such as 2+2, 3+1, 3+2, and different type of collaboration with the international partners. On the other hand, we also have global engineering, which allow our students to study abroad, and several of faculty here has been actively involved in this program. So this is obviously just one of the important part of this global education program, and particularly that is sponsored by one of our donors which allows this to happen in this summer. So totally we have 8 seminars from July to from June to July. So in the June we already have 4, and then starting from this week we have the other 4 here. So I on the announcement, if you are interested in the rest of the talks, so you can always click RSVP. So this way you will be receiving emails, notification about what's the coming talks. And also we will make all these previous talks, the video available on our college website, as well as on college YouTube channels. And I'm glad to report back that after our talks, we have received quite a lot requests from our former alumni, students from Europe, and Asia. They requested for the for the videos. The reason for that was now it's a globally timing. We are in Detroit, it's sort of in the morning, but in Asia right now it's a late evening. It's because of the timing. Not everybody can be online at the same time. So before I turn to the last thing I want to thanks is this part of this global education was sponsored by the Nancy Philippart and the Thomas McGill Center for Global Education that they have been very generous to support us and set up this global education center at the College of Engineering. All right, so with that said, today, as I mentioned earlier, it's the 5th edition of this talk series. So we are very fortunate and happy to have our rising star, Dr. Azad Ghaffari from mechanical engineering, to talk about the structured and scalable safety control of autonomous ground and aerial vehicles. And one thing I want to point out that the reason we have this, is, as you can see that today, in the modern age, I would say the difference or the boundary of these disciplines are really getting blurred. For example, Dr. Ghaffari was trained purely in the control. Normally, you will see control people were sitting in the ECE department, but he's working on distributed control system and allowed to do all kinds of optimization and etc. But he's in the mechanical engineering because in many cases that you need to do the optimization that in this mechanical components as well. So I think that as you probably have seen, if you have attended the previous talks, you will see that today, based on the talk title, you actually, if I don't tell you that which department this particular speaker come from, so you probably don't even know that. So I think that that's the reason why we have this, is as an education engineering in computer science, in these disciplines, the future world really needs this kind of that, you know, across the multiple disciplinaries. So I think it's really good for you guys, for you guys to listen to this talk and then see the same problem from the different perspectives. For example, we at the computer science, our lab is also working on ground and aerial vehicles. At the ISE, we also have faculty working on UAVs and etc. But it's all from different, different perspectives. I think this is the key for that for the future education of engineering. So without further ado, I will turn the podium to Dr. Ghaffari. So Azad, go ahead.
Yeah, thank you, Wei-Sang. Thank you for the introduction, and it's a pleasure to be here and to stress Wei-Sang's point. So we are living in an age that so you cannot actually specify which area you actually are dealing with in terms of multidisciplinary problems. So particularly in this presentation today, I will be talking about the way that we actually design controllers, specifically safety controllers for autonomous ground and aerial vehicles. And our focus is actually on developing controllers that are structured and scalable. To this end, so we go back, look at the history of autonomous vehicles. So the first autonomous ground vehicle actually was developed in 1977. So it has been almost 45 years, and we have seen dramatic changes in the technology. And these days we have multiple companies that are involved in this technology. Most notably is Tesla, which is actually famous for their electric vehicles with autonomous features. So when we talk about autonomy, so there are different levels of classification, but by ASAE, which actually divides the automation in two levels. So the first three levels, 0, 1, 2, are basically there is the driver who is in charge of the vehicle, but the third and the fourth, fifth level, so we have extensive levels of autonomy in the autonomous vehicle. So in this talk specifically, we are targeting some problems which can contribute to the autonomy level 3, 4, and 5. Specifically, we consider the problem of trajectory tracking, obstacle avoidance, for example, geofencing. And this is just one side of the problem. So the other side of the problem that we also will be discussing is the quadrotors or unmanned aerial vehicles. And it may surprise many, the first version of quadrotors, actually, it was built around 1920s. So you see a picture of this demonstration. It was one of the first attempts, actually. The rotorcraft actually flew almost 50 centimeters above the ground, which was a phenomenal achievement at that time with the technology. However, you see, you have almost 100 years in between. The technology has changed dramatically again, especially during the last 15 years. We have seen the technology of the drones and quadrotors have exploded to the extent that these days we actually have passenger drones. For example, we have multiple companies in Asia, in the US actually. So the one that you see here, this is a prototype back last year actually. And then it can fly for almost 20 minutes. So that is still in infancy stages. So the passenger drones specifically, they can actually contribute to solving mobility problems, especially in the urban areas, because they can actually provide like they can provide immediate relief to actually to reduce traffic congestion in the future world. So what is the problem that we are actually trying to solve here? So if you have a vehicle, so either it's a UAV or a ground vehicle, so it can operate inside an environment. So, but the environment actually has multiple obstacles. So the obstacles, they can be stationary, they can be dynamic obstacles. And then in this demonstration, you can see that the UAV actually is shown in two different representations. The left one is actually the area vehicle representation, meaning that, so if you have a accurate model for the vehicle, so you can actually incorporate those boundaries, those limitations in the design process. However, that complicates the problem dramatically. So that's why we, in many cases, we see that the researchers actually opt out for the point of vehicle representation, which is shown at the right-hand side. That means that you are actually treating the vehicle as a point. So, but again, if you look at tight maneuvers, for example, if you look, if you want to park a vehicle, so that has a different treatment. So obviously in that case, we cannot actually use the point vehicle representation. However, for this research, we are using the point vehicle representation, and the path that the vehicle takes is actually a curve that is going through the walled space, which is the environment that the vehicle operates inside. So you go from a starting point to a goal point. There is a stark difference between term trajectory and path. So path, as I said, it is the curve that connects the starting point to the goal point. However, the trajectory is including the temporal information. So because we have dynamic also properties associated with the vehicle, so that means the trajectory is differentially constrained by vehicle's equation. So and then what we are doing here is actually we are trying to find a safe passage from the start point to the goal point, incorporating the dynamic behavior of the vehicle. So if you look at the literature, so the motion planning problem constitutes a variational calculus problem. And it has analytical solution only for the simplest cases. So, so that's why you cannot expect an exact solution for general situation. And to this end, many approximation methodologies have been developed actually to come up with the with proper algorithms for motion planning. And many of these algorithms actually they use the decomposition approach. So by decomposition approach, actually we have 4 levels. So first, the path planning problem is solved by approximation. And then, so obviously the approximation needs to be smoothened out. And then when you are, we have the smoothened path, then we actually find the trajectory that conforms to the path. And then again, we note that the dynamic properties of the vehicle has to be incorporated into the trajectory. So that means we have some dynamic constraints attached to the trajectory. And ultimately, when we have the trajectory figured out, there is a control loop that actually takes the vehicle through the environment on the safe trajectory. So, but if you look at the problem, so the motion planning, trajectory planning, path planning, so all of this phrases actually they have been used interchangeably. So these methodologies, because of the way that you solve the problems, they are numerically intractable. So it means if the number of obstacles increases, the dynamic constraints in the environment increases, so the solution takes longer to actually converge. So to the end that in many cases, you cannot actually perform agile maneuvers in the environment. And then if we add additional complexity because of limited speed and acceleration, the problem even becomes more complicated. So that's why many researchers, they have opted out for feedback control to utilize the different feedback methodologies to navigate among an obstacle environment. So the difference that this methodology has with the comparison with the existing motion planning methodologies is basically you are not creating the safe trajectory. What we are creating is actually the safe control commons that allows the vehicle to safely maneuver inside the obstacle environment. So the popular methods that have been tried for so using feedback control to achieve safety control. So there are many class of methodologies. I have listed 4 of them here because of the relevance that it has to the work that we have done. So first methodology that has been tried out, it is artificial potential fields. This is one of the earliest methodologies, has been around for almost 50 years now. Primarily, it was used to actually implement safety constraints in robot manipulators, but it found its way to actually autonomous robots. So this methodology is agile, but the problem is if you have multiple obstacles or a complicated environment, so we need to have navigation functions which are not easy to obtain, so that actually limits the capability of the artificial potential fields in reality. So the other class of methods that have been tried are based on mathematical programming. So these methodologies, they actually create a constraint optimization. So they have standardized the formulation, but the problem, again, you have numerical limitation. They require high processing power. So that's why the application reality is somehow limited. And one branch of mathematical programming it has been very successful in control applications is model predictive control. This again constitutes a constrained optimization. It has been heavily explored, but we are still facing curse of dimensionality. So meaning that if the order of the system increases, the environment becomes more complicated. So now we have to spend a considerable amount of time processing the data and calculating the control commands. So the last methodology that has been recently explored is based on barrier certificates and functions. So these functions, they are very successful at actually modeling safety constraints, and they can be used in conjunctions with other methodologies. For example, you can use them with quadratic programming, so you can incorporate them with model predictive control. However, there is a catch with this methodology. So the construction methods for the barrier functions are limited. So as you see, for any methodology that we are actually exploring, there are some pros and some cons. So, but at the moment, because of the capability that the barrier certificates provide, and they have been recently explored, so we actually select the barrier certificates, work on these functions to create the safety constraints for our problems. So the design objectives that we have here in this talk, it's basically to create analytically driven safety control algorithms. We want to minimize the numerical demand of the algorithm as much as possible. And to that end, we allocate dedicated control modules with specified structures for various design criteria. And the various design criteria comes into play because we are dealing with a safety control situation. So you have, for example, a trajectory to follow, and then you have to also avoid obstacles. There are also some constraints attached to the system that we are dealing with. So that means we have multiple design criteria. We have a multi-objective problem to deal with. So we use barrier functions to model safety constraints. And then we actually draw explicit relations for these barrier functions, which allow us to create assignable control structures, safety control structures. And also the structure that we provide are parameterized. So that means the calibration and the design process becomes much easier because we have a limited number of control parameters that we can tune them in a automatic manner, and that actually allows us to save time on design and calibration. So the control structure is modular, which reduces design complexity and improves scalability. Scalability is important because when you have a autonomous system in a cyber physical situation, so the number of vehicles are too many. So the number of obstacles, too many again. So it is important to have the control scalable because you don't want something which is super complicated. So if something changes with the vehicle or something changes in the environment, we need to have something which is easy to calibrate and tune. So that's why the scalability is important and we highlight it here. So the outline of this presentation, I divided in two sections. So we first talk about the ground vehicles, which they have actuator delay. So the actuator delay in reality, it actually is translated into a limited thrust, a limited torque. So the objective here is we want to create agile safety control independent of the obstacle environment. So the solution that we provide for this problem is to create explicit safety bounds using barrier certificates, and to compensate the delay on the actuator, we actually provide a two-layer Smith predictor, which we have shown in our experiments. It improves the transient performance of the algorithm considerably. The second part of the presentation, I talk about unmanned aerial vehicles. In this situation, we have limited thrust and torque. And our objective is actually to derive a analytical safety control for a geofencing application. So the geofencing application is another safety critical scenario. So that means you have a safe net which you want to cast around the vehicle. So how to actually design the control that allows us to achieve the geofencing without challenging the control bounds of the vehicle. So the solution that we have here is based on a modular safety barrier. And then we also use nonlinear robust control to achieve the desired trajectory tracking that we anticipate. So let's go into the first part of the presentation. So first is the ground vehicles. So our problem is to look at the safety control for ground vehicles. So, but there are some constraints attached with this ground vehicle. So first and foremost, in many situations, we have time delay acting on the actuator. So it means if you actually apply or actuate a specific control command, it takes some time to see the result at the output. On top of that, the ground vehicles that we have, they have under-actuated dynamics. So that actually complicates the control problem further. On top of that, we also have multiple obstacles. So it's not that we are looking at a single obstacle. So we have multiple obstacles, and then the obstacles, they can take different shapes. So for example, it could be an object or it could be a wall. So the methodology, we are using a nested modularity with integrated safety. And our solution is twofold. So we have first the two-layer Smith predictor, which allows us to compensate the time delay in the actuator. And the second contribution is the explicit safety control bounds that we found for the heading angles, which actually guarantees the safe performance of the vehicle in the obstacle environment. So the vehicle that we have in our lab, and then we base our study on this specific robot. It's a non-holonomic mobile robot. It has a differential drive, and it is equipped with multiple sensors, velocity measurement, acceleration, and for example, bump sensors, cliff sensors. So the kinematic model of this vehicle is quite, if you look at it, it's a third order equation, and it has been one of the benchmark problems in control area in many papers. It has many interesting features. First of all, it has a non-holonomic constraint, which makes the control problem super interesting to analyze. So, and then on top of that, so you have a servo system which actually drives the system. So the servo system in this situation, it is comprised of two DC motors, and the DC motors, we can pretty accurate, actually very accurately model them as linear models. As you see here, we have the linear and the angular velocity, V and omega. They are actually connected to the thrust and torque through the transfer function that you see. And these transfer functions, as you see them, they are similar, identical. And that is because of the properties of the DC motors. So as you notice here, we have the time delay in this equation, and that time delay actually shows up in the input. So that means when we actually change the velocity, the voltage of the DC motors, it takes some time to get the torque and the acceleration that we want. So let's look at the nested modularity structure that we provide here. So we have 3 control modules. Each module takes care of a different objective. So first, we have a vector field orientation algorithm. This is for precision trajectory tracking. So from this algorithm, we actually calculate the desirable values of the linear and angular velocity from the position error. And then these values are used to actually create the desirable values for the left and right wheels. And then using an inner velocity control loop, we can actually get the tracking performance that we want. However, because of the delay that appears in this application, so if you just use the VFO, the performance is not good. So for example, in our experiments, we have seen that if you do not compensate the time delay, it takes up to 30 seconds, for example, to go through the transient, which is not an acceptable performance. So that's why we propose a 2-layer Smith predictor to compensate the time delay. because of the structure of the system, we have velocity control loops. We have a separate heading, a control loop for heading angle. So that's why we have one layer for each of these control loops, one for the velocity and the other one for the heading angle. And the last part of the algorithm, which is the safety module, it comes into play. We actually use barrier certificates to obtain explicit bounds on safe heading angles. So to this end, we actually enforce exponential decay on the barrier functions. And from this step, we get the safety filter, which we can actually incorporate in the design. And we show that the performance is actually it surpasses the existing competition. So let's look at the first module that we are presenting here. So the first module is the taking care of the trajectory tracking. So if you look at this demonstration here, so we have a red dot. The red dot represents the robot. So the green dot represents the reference trajectory or reference path. So the green arrow is the velocity, the reference velocity vector. So it has a magnitude of VR, and then the heading, which is theta r. So the objective is actually to align the red vector with the green vector. So if you look at the problem here, so that's not the only concern that we have, because we also have position error, which is shown as the black arrow E in this demonstration. So now what we can do is actually we can compromise. So we can design the control such that we can push the vehicle along the purple vector. And if we do so, so it means we are taking care of, so the first objective, which is aligning the red vector with the green vector. And the second objective is actually reducing the error. So that is that purple vector. It actually gives, it is obtained through this calculation that you see in the left-hand side, which is shown as vector H, and that is the convergence vector field. So H vector, if you look at the magnitude is VA. So that is the pushing control. So it means we need to push the vehicle this much. And then the orientation is theta A. So it means we need to adjust the orientation of the vehicle this much to get close to the desired, to the reference trajectory. So when we have the orienting control, we can actually use a PI or another form of control to get the desirable angular velocity. So as shown as omega A at the bottom of this page. So when we have VA and omega A, so that means we can actually use these values to find the proper reference velocities for the left and right wheels of the vehicle, and then get the performance that we want. So if you
Azad, can I ask a quick question?
Okay,
the green arrow is tangential to the path.
Yes. So the path, if you look at the dashed black line, so that is the reference trajectory. So the green arrow is tangent to that reference trajectory.
Thank you.
Yeah, thank you, Chinan. Okay, any other question? Okay, so as I was saying, so the differential drive servo system comprised of 2 DC motors. So this guys, you can pretty much use the linear models to capture the dynamic behavior of this guys. And then if you look at the equations, so which are provided here for the left and right wheels, so these are 2 linear equations. So d, lowercase d, is the distance between this left and right vehicles. So when we have calculated the desirable velocities, VA and omega A, from the VFO. So we can actually calculate the desirable values for the left and right wheels velocities. And then we have an inner velocity loop basically to take care of this problem. So that actually allows us to get the performance that we want from the VFO. However, in this situation, we have time delay. So when you have time delay, so VFO cannot actually get the performance that you are after, because we are actually changing the control signal, but the result shows up, for example, half a second later, a second later. So half a second may not look much, but it messes up the entire performance of the system. So that's why we propose a two-layer Smith predictor. So what is a Smith predictor? So Smith predictor, it has been around for many years. I think almost now 60 years. So it has a pretty ingenious design. So if you look at this block diagram that you see here, so disregard this, the red, the blue, and the green paths that you see here. So the actual system is shown as G times e to the power of minus tau s. So that's the actual system, which is comprised of a linear transfer function plus a time delay. The time delay stands for the actuator delay. So we have a controller shown as block C. So if you just want to wrap a feedback around this system, so just the traditional methodology is just to go for the red path. So disregard the blue and the green path. We have the red path. If you look at the closed loop transfer function just with the presence of the red feedback, so you see that the time delay term will show up in the denominator of the closed loop transfer function. So this is a infinite order transfer function, and this time delay actually messes up the location of the poles of the closed loop system, and to the point that it becomes almost impossible to get the controller right to actually to get the performance that we want. So that's why Smith came up with this ingenious idea. So what if we actually replicate a nominal model of the system, and then we feed this feedbacks to the actual feedback, and that way we can actually push the delay all the way outside of the feedback loop. So when we have done so, if you look at the outcome, which is shown in this big green box here, so you see that now, so considering we need them to make the assumption that the nominal model that we have for the actual system is fairly accurate. So G hat and tau hat are closely matched with the actual system. So if that assumption holds with the Smith predictor, as you see, the time delay has pushed all the way outside of this feedback loop. So that means now you have CG over 1 plus CG. So that means you can actually use many different linear control methodologies to design C to get the desirable performance that you want. So that is the gist of Smith predictor. So it has been explored by many researchers, and still to this day, people actually come up with different ideas to improve upon the Smith predictor. So I just want to wait a second. So if there is any question or somebody wants to need any discussion about the topics that I have gone through so far, I would be happy to discuss. Otherwise, I can wait until the end. Okay, so that sounds good. So now with this, so we have the Smith predictor. So the Smith predictor takes care of the delay in just a single loop. So if you look at the non-holonomic mobile robot, it actually is comprised of two major loops. So one is the velocity loop, which takes care of the servo system. The other one is, actually we have three loops. So the other loop is, it takes care of the heading angle, and the outermost loop is the VFO, which takes care of the position error. So with this arrangement, so we have to actually properly arrange the Smith predictor in this fashion that you see here. So we have two Smith predictors for each wheel, so left and right wheels. But if you look at this configuration, so you are pushing out the delay from the velocity loop. However, the delay is not out of this picture yet. So because when we are taking feedback, so because the angle and position, actually, the delay shows up in this measurements. So that's why we need to add another layer of Smith predictor to actually compensate the delay that shows up in the heading angle. So that's why we have added the other Smith predictor as shown in this purple dashed box here. So hence we have the two-layer Smith predictor. One is actually taking care of the velocity loop, and then the other one takes care of the heading angle. And with this, actually, we have shown that the tracking performance is improved dramatically. So we have conducted multiple experiments. So one of the results that I show here is actually for a circle trajectory. So as you see here, the dashed dot blue represents the VFO without the two-layer Smith predictor. And the red curve actually shows the performance with the two-layer Smith predictor. And if you look at the right-hand side figures, so figure A and figure B, they represent the position error and the heading angle error. So as you see, the two-layer Smith predictor reduces the transient time by a factor of 4. And it's observable that you see even the angle also is performing much better. One important point here is actually the angle plays a critical role in control of non-holonomic mobile robots, because technically the velocity, so actually the position X, Y, they are affected by the heading angle. So slightest improvement in the heading angle actually improves the position tracking or the trajectory tracking dramatically. And that's why we have the two-layer Smith predictor, because with a single layer, this performance cannot be achieved. And then the position error is basically gone down considerably. So the RMS value of the position error is 1.69 centimeter, and then the average is 1.58 centimeter. So that's considering the accuracy of the measurement and the accuracy of the control comments that we have here. This is a great improvement in the trajectory tracking for this application. So we have taken care of the trajectory tracking, but still we have to deal with the safety issues. So if we have an obstacle in the environment, so how do we deal with these obstacles? Because our intention is to actually design control modules that take care of these different objectives. So the first two modules, namely we have the VFO, and then the two-layer Smith predictor, they take care of the trajectory tracking. So it means we get a precision tracking using these two modules. So now let's look at the safety issues. So the barrier certificates, they actually have the capability to map the environment into positive or unsafe zones and negative or safe valued contours. So if you look at the figures that you see in the right hand side of this slide, so you see the areas that are marked with the checked green. So those are the safe areas. So you can navigate in these areas. So the red contours around all these obstacles that marks the boundary of this each of these obstacles. So the boundary stands for a zero contour. So that's a zero contour. And then the safe levels are defined so as B negative. So it means when we have B negative, so the vehicle is safe, or so otherwise, if B becomes negative, positive, so now we are in risking of a collision. So let's look at the mathematical foundation so that we can actually use. So here we provide a basic introduction about the barrier certificate functions. So there are many different, at least I can count 4 types of barrier functions. So barrier certificates, Lyapunov certificate, Lyapunov barriers. So here we look at barrier certificate functions. So that's just to conduct our analysis. So let's consider this system given to us. It's a dynamic system. So which the state is vector is z. So the barrier certificate function is with exponential decay. So that is also an important feature because it actually enforces the safety maneuver. So the exponential decay affects the safety maneuver. So we call function phi z a barrier certificate with exponential decay if we have these 3 conditions satisfied. First of all, this function needs to be differentiable with respect to the state of the system. Second, the initial state of the system has to be inside the safe zone. So that's why phi z0 is less than 0. So we cannot have the initial state inside the unsafe zone. So the last condition, which is the most important one, is actually the rate of decay of this function along the trajectory of this system. It has to satisfy this exponential decay rate that you see here. And alpha is a constant value. It could be positive or negative, but in our discussion, we consider alpha positive. So if you have a barrier certificate function, so you can use this lemma to actually get the conditions on the states, the safe states for the system. So it tells us if phi z is a barrier certificate function and we are initially in the safe zone, so then we can prove that phi actually stays always safe for as time goes to infinity. So that is a key lemma that we use to develop our control structures, both for the ground vehicle and the aerial vehicle. So any question about this type of functions?
So I thought this third, that derivative condition, the third condition.
Okay.
I was thinking it's in a sense like the gradient method in optimization.
Yes. Okay. So you are right because so if you compare so in gradient, so if you like gradient methodology, which you can compare it with Lyapunov methodology. So for example, in Lyapunov, it says so the function itself is positive, and the derivative has to be negative definite. So, but here we have a opposing condition. So the function itself is negative and the derivative can go positive, but it cannot be. So if you look at this condition, because phi is always negative. So that means the right-hand side of the third condition is giving us a non-negative value. So that is the major difference that comes into play in comparison to the gradient method or the Lyapunov methodology.
Yeah, thank you.
Okay, you're welcome. Okay.
Hello, Azad. This is Keshin.
Okay, hi, Keshin.
Yeah, this is interesting. So, so you mentioned the Lyapunov function here. So this barrier certificate function, would that be similar to the Lyapunov function there? So do we have like a way to find this function, this type of function systematically, or
okay, yes,
by chance?
Yeah, okay. No, that's a good question. So actually, there are some construction methodologies to create the barrier certificate functions. So for example, so if you model the obstacle as a polygon, so you can actually, so there are methodologies, recent developments that you can actually get piecewise continuous approximation for each side of this polygon, and then that gives you the barrier certificate. However, this methodology involves a computational effort. So you are actually solving an optimization to get this barrier functions if you model the obstacles as polygons. So the other methodology that people they are trying to do, because this is just a recent, like maybe this started around 2007. So the first paper that started to actually discuss this kind of functions with regard to safety control, it goes back to 2007. So this is still under development. But the other methodology that has been recently explored is actually use, for example, logarithmic functions or exponential functions like the normal distributions. If you look at the so this map that you see here, so this can actually be a candidate, which is actually implemented using a normal distribution like function. So we have limitation in selection of the functions, but we can actually make assumption to make our life easier. So meaning that if you actually cast for example, consider your obstacles as certain shapes, like a circle or a rectangle. So there are already methodologies that allow you to actually get these functions. But if you have a more complicated shape, let's say if you have a bigger obstacle, concave situations, so that is still under development.
Thank you.
Okay, you're welcome. Thank you. So any other questions? Okay, so let's look at the capability that we get actually if we have a barrier certificate function. So as we have here, so if there is a barrier certificate, as I said, the boundary of the obstacle is shown as b equal to 0. So the third condition is actually giving us the exponential decay, which is shown as the first equation here. So let's say that we have this barrier function figured out for this certain situation. So we have a bunch of obstacles. We have figured out B here. So now we have the equations to actually calculate, meaning that we are interested in getting the safe envelope for the heading angle. So one assumption that we make here is the vehicle can only go forward. So this is just a moving, like a forward situation. So we cannot just come back, which is basically the assumption that we have to make when we are dealing with autonomous vehicles. So if this is the situation, now using the third assumption on the barrier certificate function, if you do some simplification, you end up with the condition that is shown in the green box. So this condition actually allows us to calculate the bounds on the safe heading angles. So so further calculation actually, so it tells us, so if you look at this inequality, so we have a cosine function less than c, and c is an expression of the barrier function, and g, which is the gradient of the barrier function. So it is a rather complicated expression. It's not just a constant value. It changes based on the position and the velocity of the vehicle. So if we are far enough from the obstacle, so this value of c is larger than 1. So it means, so this condition is always satisfied. So the heading angle is safe. So there is no need to adjust the heading angle. However, when c drops below 1, it means there is a portion of this heading angle which is not safe. So that means we have an unsafe envelope. So if we do the calculation, it turns out that we have the low and high bound of this unsafe envelope as shown here. Theta L is beta minus delta, and then theta H is beta plus delta. And if you look at the demonstration that you see at the right-hand side, so the red circle is the boundary of the obstacle, and the unsafe heading angle is shown as theta H. So it's the area between theta H and theta L. So at any moment, we have to steer away from this range of heading angles. So theta H, theta L, so we have a expression actually using this barrier functions for this bounds of the heading angle. And now using these values, you can either go left or right. So that's the choice that we have to avoid the obstacle. So if we go left, so the upper condition that you see here, so that is the calculation that we have to do to get the safe heading angle. So meaning that if the barrier certificate satisfies the third condition, so we don't make any adjustment to the heading angle that is calculated from the VFO. However, if the third condition from the barrier certificate is not satisfied, then we make an adjustment. So either we go left or right. So if we go left, it's beta plus delta for the heading angle. If we go right, it's beta minus delta for the heading angle. So with this, as you see, this is the entire algorithm that we propose here. So we have all the modules in place. So the safety filter, it sits right after the VFO. So it acts on the velocity and the angle that is found from the VFO. So we do the calculations, and there are actually some additional calculations that needs to be done, but I actually just stick with the most important parts. And then we have the angle loop here. So the steering angle control loop and the velocity control loops. And then in total, this algorithm actually has 8 tunable parameters. So that means the calibration process for this algorithm is quite easy to conduct. And then you can actually go from the innermost loop to the outermost loop. So to tune the control parameters properly. One side note is actually to get the performance that we want. So the innermost loop has to be fastest. So that's why the velocity and control loops are faster than the position control loop, which is implemented using the VFO. So if this is followed, so now we can actually look at the experiments, see what is going on. So if this actually works properly. So this algorithm can handle multiple obstacles. The control structure is the same, so we don't have to modify the control structure. The only thing that will change if the number of obstacles changes, it just is the barrier function. So the barrier function is scalable to numerous obstacles. So one candidate that is actually used here is shown as this exponential function here. And this exponential function actually relates the distances between the obstacles and the robots and then converts them to this barrier functions. And we have some constant parameters, including B0 and sigma j, which actually allows us to further tune this barrier function. So with this, so we have run extensive experiments actually. So this is one case that we have a circle reference, and then we have two obstacles sitting on the reference trajectory. And as you see, the vehicle successfully avoids the obstacle. And then on the right-hand side, the top figure, if you look, you see that the unsafe heading angle envelopes, it is marked with dashed blue and dashed green. So, and then we are actually staying outside this unsafe heading angle. And the bottom right figure actually shows the barrier function. So the barrier function has to stay negative all the time. And that's what you see here. And this is, let me see if actually I can, so. Okay, so this is a demonstration of this case, actually. You see the two obstacles that are in the environment, and the vehicle actually goes through the environment and avoids the obstacles. And because we didn't have a camera on top, actually, this is, the reference is circle, but it is distorted this way to actually to show this reference trajectory. So this is what is happening with this case. So this is the first case. So this is one of the experiments with the circular reference that we actually tried. So now if you actually look at, okay, so we have another experiments done. So this experiment actually is for the situation that we have a wall. So if you have a large obstacle, it doesn't have to be necessarily a circular obstacle. So it's a big obstacle which can represent a wall. So the same situation happens. So you can see that the algorithm tracks the reference and then safely avoids the obstacle, and the heading angle is kept outside the unsafe cone, and then the barrier certificate also stays negative all the time. So this is the wall experiments that you can see here. And please pay attention that when the vehicle gets close to the obstacle, so it actually adjusts the heading angle. You see, when it goes too far, it actually adjusts the heading angle to come back to the reference trajectory. So, and then after it passes the obstacle, it successfully goes on to track the reference trajectory. So this two experiments were among the numerous cases that we actually tried in our lab. And then, so this experiment actually concludes our discussion about the ground vehicles. So if there is any question about this case, I would be happy to answer. Otherwise, I can switch gear and then talk about the aerial application of the safety control.
Hello, Professor.
Hello.
Can I ask a question?
Yes, go ahead.
How does the robot know the information of the obstacles? It's using a map or it's sensing the obstacles?
Okay, so the obstacles are, so the information of the obstacles, because we have a stationary environment, so the map is already fed to the system. So that's how we get this done. So at the moment, there is no algorithm, for example, simultaneous localization and mapping involved in this process. So we consider a map for the environment, which means that we have already the location of the obstacles available to us.
All right, thank you, Professor.
You're welcome. Thank you.
So Azad, in the same thinking,
okay.
You know, because your optimization problem can be applied to multiple vehicles. You know,
okay.
in a multi-vehicle situation, there must be some kind of V2V communication,
okay.
something
okay. Yes,
that will do the optimization at the same time.
Yes, yes. Yeah, actually, that's a good question. And that's the problem that we are currently working on. So in that situation, so we have vehicle-to-vehicle communication, and that actually becomes very interesting because you have actually now the barrier functions moving in time, so changing in time. So that means you have a time varying situation when you have this vehicle-to-vehicle communication situation. And that is pretty interesting when you have, for example, leader follower, or you want to overtake a vehicle. So that is a necessary situation that you need to have the information. And it has been quite an interesting problem actually for us during this summer. In the lab, we have worked on this two problems. So that was a good question. Thank you, Chinan.
Yeah, thank you. Yeah, I mean, these time varying systems we've been working quite a bit these days, and
okay.
Yeah, I mean, the computation it's an issue usually.
Yes, yes, yeah, that's true, because if you have that situation, now, as you said, you end up with a sort of like, so the processing power has to be actually contained. So the processing demand has to be contained, because what we are doing, actually, we are running all these calculations on board the vehicles. So that's why for the current methodology that we are trying, we are actually looking into quadratic programming to actually, and then we actually get the conditions using barrier certificates to actually minimize the calculation that you need to solve to get the behavior that we want. But that, again, is a good point. Okay, any other question?
Hi, Professor Azad.
Hello, hi. Hi.
Hello, how are you?
Hi,
Professor, I see when you develop the control barrier functions for incomplete state information environments, for example, a crowded street, there are many vehicles, in which the state might be how the sensor's noise can be estimated there. Is it need to, for example, add another layer to the Smith predictor or not?
Okay.
Maybe I want to know.
Okay.
Do you calculate it here or not? It may be not need another layer.
Okay.
For this.
Yeah. Okay. So that's a good question. So that question can be mostly addressed in the simultaneous localization and mapping algorithms that come into play in reality, because in reality, if you have moving obstacles, a map won't be sufficient. So you have to actually extract the information from the cameras or from the LiDAR system, or if, for example, you have vehicle-to-vehicle communication. So in that situation, so now you need to actually figure out a way to beat the actually inaccuracy that comes inherent with the components that you have on board the vehicle. So the measurements, they inherently have some inaccuracy. So that part can be addressed as a separate problem in the simultaneous localization and mapping. But you are also right on the front that if you have this kind of communication, you may end up with network delay. So that network delay has also to be dealt with in a different manner, which might be adding another compensation level for the time delay on top of what you already have, because the two-layer Smith predictor considers these issues at the module level, at the vehicle level. So we do not consider the communication delay, for example. So that's also a good question, which can be actually further investigated, but we haven't studied this problem yet.
Thank you very much. Thank you.
Thank you. Thank you. Okay. So any other questions? Okay, so thank you very much. Very interesting questions. So let's look at the unmanned aerial vehicles. So the unmanned aerial vehicles, as I said, so especially this passenger drones have become quite interesting these days, especially. So I think in 2016, a company in China, Yihang, actually, they created, and then you can actually purchase this vehicle. So it's a flying passenger drone. So the price is quite high. It's $250,000 US dollars. And then you can fly actually maybe for half an hour, but that's just the start of this technology, maybe in 15 years or so. So that's another interesting thing, because in 15 years, so it has been it has been estimated that by 2035, the share of the passenger drones will be almost 35 or maybe actually 40 billion US dollars. So that's a quite big market, so which will open new areas actually to this technology. So if you have a passenger vehicle, for example, one situation is actually you want to contain this vehicle inside a safe net. So you cast a safe net around the vehicle. So for example, if you are operating in an urban setting, as it's shown in this right-hand figure, so the dashed green area, this is your safe area to actually explore. So you cannot get out of this area or get into the middle of this urban area. Or if you have a coastal situation, for example, maybe you have some structures on these islands on the right, so which you don't want, for example, civilian drones get to those areas. So that's why the geofencing problem comes into play. And the barrier certificates, they actually are quite capable of modeling such conditions. So as we talked about barrier functions, they can do they can be used for obstacle avoidance. Now we actually explore the possibility to use them actually to get this geofencing control design done. So the current methodology that uses barrier functions, they are heavily relying on the shape of the function. So that means the control actually is affected by the shape of the barrier function. So we don't want something like that, because if the shape of the geofence changes, now the barrier changes, and now when the barrier changes, the control changes. So that is not what we want. So we want something which is which has a assigned structure. So, and then that way we can actually facilitate our feasibility analysis, because in this situation we have limited thrust, we have limited actuation, and that actually brings up some new problems about feasibility analysis. So what we are proposing here is actually a modular barrier function, which actually gives us a closed form for safety control. So with this problem, again, we have some limitations. So the input, the control commons are saturated. So there is a limitation on the control common. So the system, again, is under actuated. So we have a 12th order system. However, we have 4 actuations, so that's it. So we have to deal with this property of the system. And then also on top of that, we have low position measurement. In reality, even so, if you have a GPS system, so you cannot rely on those kind of information. So it means we have low rate position measurement. So that's why we need to actually consider this limitation when we are designing the barrier function. So what we get out of this proposed solution is actually a proven, analytically proven safety and convergence for the algorithm that we have, meaning that we can actually prove analytically that we follow a given reference trajectory and we safely stay inside the geofence. And our design is, again, scalable because it has a assigned structure. And then the control laws are explicit. So this is the UAV that we have in the lab. So it is actually designed to withhold tough experimental situations which we come across in the lab because we have limited space. So this guy has interesting behaviors. As I said, it is a 12th order system. But with some interesting methodologies, you can actually convert this complicated system to 6 decoupled double integrators. So that means we can actually now look at one double integrator to analyze the behavior of this one, and then expand this in a modular fashion to get the safety control that we want. So actually this this process is done through a two-layer feedback linearization, which is a quite popular methodology. So let's look at this double integrator problem that we have here. So we start with the simplest situation. So the simplest situation is, let's say that we have the barrier position, like the position at the origin. So we want to maintain the position always below the origin, meaning that we want to make the position always negative. And then keep in mind that in this situation, the acceleration is limited. So because we have limited resources, we cannot actually accelerate or decelerate infinitely. So as I said, the design limit is, so the problem is to design the safe limits of the acceleration such that the position stays negative for all feasible initial conditions. So again, this is important because x less than 0 includes many, like half of the space. So, but half of the space, it's not a feasible, some of them are not feasible initial conditions. So that's another thing that we need to take into consideration. And then what we do actually, we offer to incorporate these, the control saturation into the shape of the safety barrier that we obtain. So if you look at this double integrator, because it has limited acceleration and deceleration, so if you actually sit inside this gray area, so, and then you can actually go to the origin and stay inside the shaded area with the limited acceleration and deceleration you have. So it means if you are in the shaded area, so if you accelerate or decelerate, so you can actually stay in the shaded area. However, if we pick a point above this dashed red line and between the vertical axis and between the dashed red line, so no matter what you do, so the safety is compromised because the system will go to the other side of the vertical axis. So that's the safe, the feasible initial condition that we have to deal with, which is shown as the shaded area. So, however, there is a problem with this safety barrier here. So if you look at this barrier function, and then if you arrive on this barrier function, which is shown as the dashed red line, so you don't stop at the origin. So it means if you arrive there, so you actually may go to the right-hand side. So because if you have some uncertainty or disturbance, it definitely may cause you to go to the unsafe side. So, or even if you don't have uncertainty, you won't stop at the origin. So stopping at the origin is important because we have to also prove the convergence of the algorithm. So if we are to track a reference trajectory, we have to know at each moment where we are staying at. So that's why we need to actually modify this barrier function such that if we arrive at the barrier function, we can actually show that the system stays at the origin. For this purpose, actually, we look into some modification methodologies. So if you look at the functions that are drawn in this plot here in the bottom of this page, so you have a dash blue, dash black, and then green, and then the red one is the curve that we have found. So which actually does not let the vehicle to stop at the origin. However, the other vehicles, the other curves that are actually they stand for beta x. So beta x is the function that represents these three other curves. So in this situation, we have a constant parameter rho, which actually changes the shape of this function. So as you see, if you decrease rho, make it small, you can actually get as close as possible to the actual barrier that we found initially. But the difference is here, if you actually look at the equation, especially around the origin, if you just do some linearization, you can see that the approximation, it is v plus square root of gamma over rho times x equal to 0. And because the square root of gamma over rho is a positive value, you know that this equation gives you a stable motion. It means the position will stop at the origin. So this function that we have here is actually giving us two things. One is actually giving us the feasible initial conditions, and the second is actually giving us a stable motion, meaning that we will stop at the origin. So to do this right, we actually just present this in a proper mathematical form. And then please note, you see that h is a step function, However, if you look into mathematical properties of this proposed function, this is a continuously differentiable function. So with this barrier function, if we actually obtain the control commons, so we can see that the safe breaking common decreases as the system approaches the origin. And that means we can actually keep the vehicle to stop at the origin. So that's a key property that we actually need to get the performance that we want from our trajectory tracking. So this is the first result that we present regarding this safety feature. So first, we know that the input is saturated between minus mu and mu. Mu is a positive value. So, and then we know that B, which we found in the previous slide, is a barrier function for the double integrator that we have actually discussed. And then if you look at the safe set of this barrier function, it is shown as omega, capital omega here. And then we go through the mathematical analysis, and then we get the safe bounds on the control command. So meaning that if we maintain the control command always less than US, which is shown as this expression in the middle of page, we can show that the safe set omega is forward invariant for all time larger than 0. Meaning that forward invariant means if you start inside that set, you stay inside the set forever. So that means the safety is satisfied. On top of that, another cool property that comes with this barrier function is basically telling us the function US is always larger than minus mu. So that is why this actually allows us to use the function, the expression that we have found as a standalone block in our control design. So because we know that the control value always satisfies the limits of the actual system. So we have this now. If you have this limit on the control, so obviously it actually gives you safety. How about the convergence? So because that was among our initial considerations, because safety is not alone in just one objective. So the second objective is we have is basically we need to converge to the origin, so to maintain the tracking at an accurate level. So for that, so we actually modify the control signal using the saturation function that is provided here. So if you look at this saturation function, so the saturation function actually represents the actual actuator that we have, which actually is between minus mu and mu. And now the part that goes inside the saturation block is a minimum function. So which is the minimum of UR, which is a function that comes from a kind of a trajectory tracking algorithm. And it doesn't matter what kind of trajectory tracking you are using. And then you have US, which is actually found from the previous theorem, which is the upper bound of the safety control that we have found. So if we have this control block implemented inside our system, we have both safety and we also converge to the desired position, as long as the desired position stays inside the feasible area. So what are the benefits of this algorithm, this expression that we have provided here? First of all, it has a closed form expression. So, so when we have a closed form expression, the implementation is quite easy. So it has only 3 safety control parameters. We have gamma, we have alpha, we have rho. All of them are positive. So we can tune them. They affect the convergence and the safety maneuver of the vehicle. And on top of that, because we have all of this, we have closed loop expression, we have limited parameters. So the control is scalable. So that means it's easy to tune and implement on an actual system. So with this, okay, so before I move on, so any question about this first part of this geofencing problem? Okay, so no question. So let's see. So in reality, so you may want actually to limit the vehicle between, like it's not just open-ended situation. So you just have to actually maintain the position between a low and a high value. So now, because we have this barrier function, it has a modular structure. We have found this for x less than 0. So now actually we can play with this, like we can shift this function to left and right actually to get the barrier functions to maintain the vehicle inside a upper and lower position. So as you see with this modification, so the shaded area is the safe set when we have a lower and an upper limit for position. And then the safe set, it becomes obviously a little more complicated to express, but nevertheless, it has a defined shape. So, and then from this, we can actually find the keep in safety design when we want to maintain the position between a low and a high limit. So this is the shape that we get. This is the expression that we get for our control signal. So it has a nested saturation function. So we have one saturation nested inside another saturation. So the outer saturation function represents the actuator which comes with the system. So we represent it here mathematically to reflect this fact that the system has limited actuation. So the inner saturation function is actually maintaining the vehicle safely inside the low and high, between the low and high position values. And then the innermost part of this saturation, which is UR, is the reference tracking, or the trajectory tracking. And as we said, this trajectory tracking algorithm can come from any design that you have. It could be nonlinear, sliding mode, PI, or whatever, PID. So it doesn't matter. As long as you have the control commons for the trajectory tracking at your disposal, just plug it here, and the rest is ensured that you get the safety that you want. And that's a big plus, because you don't want to redesign the trajectory control algorithm that you have, because if you have, let's say, a bunch of vehicles, so why do you actually want to redesign the trajectory tracking if it performs right? So you just plug the safety block inside the algorithm. So the tracking algorithm that we have used here is based on super twisting algorithm. And that's not the focus of this work. If somebody is interested, we can talk after the meeting, but I just mentioned for sake of argument, that we have actually used super twisting algorithm to get the performance right for the trajectory tracking. We also use the PID, different variations of PID design, but the super twisting by far is the best performance that we have got so far. So this is the summary of our control design for the UAV. So we have a control, we have a system which is under-actuated. It has 6 degrees of freedom. So it's a 12th order system, 6 degree of freedom, 4 actuators. We use a 2 feedback linearization to convert this guy to a 6 double integrator. They are actually decoupled double integrators. So we control we use the attitude and thrust. So meaning we use the rotation and thrust to control the trajectory. And then we use the roll, pitch, and yaw torques to actually control the attitude, meaning the orientation of the vehicle. So because the UAV is controlled through, the trajectory is controlled through attitude, so the attitude loop has to be faster than the trajectory tracking loop. So the modular design allows us basically similar safety control structure for all the translational axes. So this is the block diagram that we have. And as you see, the safety control actually sits in between here. So it does not mess up any part of the design that we have here. And as I mentioned, the attitude control, it is actually faster than the trajectory tracking control by a factor at least 5. Because if it's slow enough, so it means, because you are actually producing torque by rotating properly. So it means you need to actually rotate fast enough to create the torque that you like. So that's why the inner loop has to be faster. So this is the hardware configuration that we have. As you see, the lab that we have is not that big. So hopefully we can convince the department to give us a bigger space. So down the road when we expand our experiments. So we have a control loop which runs at 1,000 Hertz. So the motion capture system it runs at 100 Hertz. So that means the position information is updated 10 times less than the control loop. So we have on board IMUs, complementary filters are used actually to improve the position estimation that we have here. And then we have 2 actually cases presented here. So one case is a pilot produced reference trajectory. So this one actually is conducted to test the robustness of the algorithm. So if we actually change the reference, so what is happening with the algorithm? Does this algorithm survive this changes that is produced by the user? And the other application is when you have a priori reference trajectory. So let's see what is happening. So this is the first case. So at the figure A, it actually changes, it shows the variation of the position of the vehicle. So Z, which is the vertical axis, is limited between 0 and 75 centimeter. And the horizontal axis, X and Y, they are actually limited. The motion is limited between -35 plus 35 centimeter. And the user does not know this, and then he changes the reference. If you look at the dashed black line in figure A, so that is the reference that is produced by the user. However, because we have the safety algorithm, so you see that the vehicle does not violate the safety bounds that we have here. And most of this credit actually goes to the way that we are actually changing the limits on the acceleration. Because if you look at the right-hand figure, figure B, you see that for axis X and axis Y, when we calculate the allowable acceleration or deceleration, for these 2 axes, you can see that the dashed red bounds, they give us the safe limits on acceleration, and the green values, as you see, when the vehicle gets close to one of these axes, So the green value is the acceleration that is produced by the reference trajectory, which is not safe, but the algorithm chops it off, and then we can actually maintain the vehicle inside the safe zone. And then on top of that, if you look at the behavior of the Z, because we are doing these maneuvers along XY axis, so the vertical axis stays rather stable. So that means our algorithm is both robust to changes in X and Y axis, and then it is also safe, meaning that we can actually guarantee that the vehicle stays inside the safe zone, regardless of the changes that are forced by the user. So the second experiment that we have is actually the case that the reference is already known. We have a priori reference. So the reference, we have a black dot here. So if you look at the black dot, that's the hover position. So we bring the vehicle to this hover position, and then we go a spiral. Actually, if you look at the dashed black line, so that creates a spiral, but that spiral actually goes outside the geofence that we have put around this vehicle. So, but because of the safety control, the vehicle actually is maintained inside this geofence. And then if you look at the right-hand figure, X and Y, so the safe limit on X and Y is 35 centimeter. And then you see that the algorithm successfully maintains the X and Y at the predefined limit. And the Z also is maintained at 35 centimeter, despite the fact that the reference actually goes to 100 centimeter. And then the accuracy actually is quite good here. So we have a 95% accuracy for the reference. And the same thing, because we are actually playing with the limits on the acceleration, you can see at the moment, so that the Z-axis goes above the allowed limit, which is 35 centimeter. So the value that is produced by the trajectory tracking algorithm is green, which is way above the safe limit. So the algorithm chops down this to a lower value, which maintains the algorithm inside the geofence. And also, one other thing that worth mentioning, similar to the ground vehicle, the attitude actually plays a key role in the performance of the system. And as I said, the attitude control is almost 5 times faster than the, okay. Okay, sorry, I think, can you hear me? Hello?
Yes.
Okay, sorry, I think I lost my iPad, so I continue from my laptop actually. So let me go to the slide. So, okay, so this is, okay, so as I was saying, so this is the performance that we get from the, actually the attitude control. And as you see, the attitude actually tracks the reference attitude quite accurately. So, and then the RMS error for the roll and pitch is less than 1 degree. So that's quite good. And then at the end, so this is our work that we did during this past 2 years. It's a summary of what we did. So we are undergoing some also changes because of this COVID, so going back to school. So, I actually take this moment to thank Wayne State University to provide the environment for us to conduct this research. And with this, actually, I want to say a little bit about our university. So Wayne State has been established in 1868. We have been in Detroit area for more than 150 years. And we are proudly serving more than 26,000 students, mostly from Detroit. We have a diverse population, minorities, so many different groups. And then we, in the College of Engineering, We have 130 full faculty members. We serve 3,700 students from different backgrounds. And in the Department of Mechanical Engineering, which is the department that I'm associated with, we have 17 faculty members, and then we anticipate to have some new faculties for the coming years. Our research areas are in three main thrust areas: advanced materials and manufacturing, advanced propulsion and energy systems, and noise and vibration control. Obviously, my area fits with the noise and vibration control. And then I would like to encourage you, if you have any interest in our research, or if you want to get in touch with Wayne State University, please feel free, don't be shy. So reach out by email or through other channels that are available. I would be more than happy to discuss our research. And this is our lab at the Mechanical Engineering Department. With this, I conclude this presentation, and I hope you enjoyed this talk. Thank you very much for your patience.
Thank you, Azad. I
you.
think that the talk is great, and you have theory, you have system, and we already have some discussions during this process. So now the floor is open to everybody, from the audience. If you want to ask questions, please just unmute yourself and go ahead and ask.
So, sir, I have a question on your ground vehicles formulation.
Okay.
I think you basically consider the kinematics problem. How much more complex would the problem be if we actually have to consider the vehicle dynamics, such as, for example, torque applied to the wheels, either accelerating or decelerating through braking?
Okay. Yeah, okay, so that's an interesting question. Yeah, actually what we have here, so because the vehicle is not super complicated, it's mostly modeled as the kinematics. It's true that we have the equation for the servo system, but the servo system here is just a DC motor. But yeah, okay, so if we have a higher order system, meaning that, so here we have a third order system. So if we go a higher order system, so there are actually solutions that we can get the barrier functions. First, we need to actually come up with some transformation. So one of the methodologies that is out there, so it's a recent methodology, you can actually find a diffeomorphism that actually converts the system to a chain of integrators. For example, if you have a fourth order system or a fifth order system, so if you come up with this transformation, you have this diffeomorphism. This is a chain of integrators. So now there are methodologies actually that allow us to get the barrier functions with incorporated safety already embedded in them. So that is one methodology, obviously. So the problem becomes more complicated because getting a closed form solution at this situation is almost, I don't want to say it's impossible, but it's a challenging problem. So that's why if you have that situation, one of the promising roads to take is actually to opt out for example, a quadratic programming, meaning that if you have a module that takes care of tracking or whatever stability, and then if you have a module that takes care of safety, so you can actually bring them together using a quadratic programming. So unlike MPC or other numerical optimization methodologies, quadratic programming actually allows us to have agile algorithms to get the solution that we want. Obviously, the end result, again, it's not a closed form solution, but it will be a numerically viable methodology to pursue in such situations.
Okay. Yeah, this is interesting because from a practical viewpoint,
okay.
For example, for motor companies' evasive steering system, you try to avoid an obstacle or a person or kid or something, the vehicle's dynamics is limited. I mean,
yes,
you cannot You cannot make, for example, a zero radius of curvature turn. That is not possible, right?
That's true.
And the torque, the amount of torque that is required for that kind of maneuvering, it's also limited. By it's different from each vehicle to each vehicle, and some higher CG vehicles can also experience rolling instability when you turn too fast, and or when you brake too fast or something like that. And these are all very practical limitations that I think are interesting to consider.
That's a very good point. Thank you.
Yeah, thank you very much.
Thank you, Gina.
Thank you. Any other question from the audience? So I have a question to you, Azad.
Yes, hi.
When I took a tour of your lab. That is pretty cool. Before.
Yes.
My question to you is your students when they're working, on this, where do you start from? For example, did you get some open source somewhere so that this ground vehicle UAVs they can start talking together? So basically, this is a this is a global education. I want to share with you some of your.
Yeah, actually, that's a good point. So there are actually So any questions? Okay, so there are actually two methods that people have actually tried. So, for example, there are ROS out there. So many people actually use this to actually build this kind of experiments to design the codes as open source. What we have in the lab is actually a fast prototyping system that we have, which actually creates executable codes from MATLAB Simulink files. So that's what we have in our lab, which actually allows us to facilitate to ramp up the students better, so in a faster pace to the requirement that we have in the lab. And then what I personally do actually with the students, I sit down with them and then actually I start with the most basic examples. So basically write some simple codes to maybe just move the vehicles or do some basic maneuvers. And then it takes quite some time. I think, but I have found this hands-on methodology much better to educate the students, because if you jump right to the mathematical side, so for students who come from undergraduate without any master's degree, so that's quite tough. But if you have a master's student, so that is a different story. So, but again, so you need to also take precaution, because the students also, they need to be prepared or come with a mindset that are open to actually learn, for example, MATLAB and Simulink in our lab. Because if you don't have the adequate background, or if you don't have the willingness to actually to pursue these avenues, it will be a little tough, because just creating algorithms and doing numerical simulation, it might not be the best way to pursue, to create solutions for such problems.
Yeah. Azad?
Yes, hi, Emmanuel.
Yes. Yeah, okay. Just a very quick points.
Okay.
I think maybe it was a slip of tongue. You did mention about the small d. You said it was the distance between the two vehicles. No, I believe it's the distance between the two wheels.
Okay, yes, right. Okay. Yes, you are right. Thank you for the correction. Yes,
yes, then there was the equation for that function, capital B.
Okay.
The capital B, because you had defined it as a function of X and Y, obviously you are considering a situation of a plane, movement in 2 dimensions.
Yeah, it's a 2-dimensional movement, yes.
So what you wrote, you got the total differential of that function by saying the b dx, then times x dot, then plus the b dy times y dot, And then you said it's equal to a constant of proportionality times the function. I mean, suggesting that that's an exponential function because it's the one that, or one of those who satisfy that property. So I wanted to know where you are. I mean, did you write that equation because you had selected the exponential function, or it was from another source?
So so the shape of the function is independent of the exponential decay that we have. So the way the reason that we actually selected this barrier function for our application, it's because of its simplicity. So there are other options out there. For example, so you can use logarithmic functions or some other like reciprocal functions, for example, to go for the barrier functions. So this specific barrier function that we have used here in literature is known as zeroing barrier function. So if this is what you want, it gives you the safety using this third inequality that you discussed already. So, but if you have a reciprocal function, so that inequality is no longer valid. So that actually changes. So you have to go for another inequality, which actually tells you that the derivative of your barrier function is proportional to the reciprocal of the actual barrier function. So that's hence the naming, the reciprocal. In this situation, it is zeroing because it allows the function actually to go to zero, the derivative actually to go to zero. So there are two main actually different areas that you can explore. But this method we use, this function we use because of its simplicity.
Okay, thank you very much.
Thank you, Emmanuel.
Yeah.
Hi, Professor.
Okay, yes, go ahead.
Can I ask one more question about that? As you mentioned, that some people use ROS to develop the algorithm. Some and your lab you are using the MATLAB and Simulink. So I actually I used the ROS and MATLAB before, so I know the both two software like or platform. So I'm just very curious about are you using the code generation method in the MATLAB to implement your algorithm?
Okay. So that's a good question. So the engine that we use actually is Quark, which is from Quanser. So this is a proprietary engine actually. So that actually creates the C codes that we actually download onto our equipment. So we write, for example, M files, Simulink files, and then this engine actually converts the codes that we have to executable files, which we actually download to the vehicles. So that is similar if you are familiar with DSpace products. So those guys, they have also something similar. So in that situation, so you have another engine, which actually you can convert MATLAB and Simulink files and then put them on the vehicles that you have. So our engine is a proprietary engine. We are not just so of course it uses the embedded coders or MATLAB coders, Simulink coder. It has to be there to actually to produce this codes, but the bulk of the engine is proprietary. It's Quark from Quanser.
Okay, got it. Thank you, Professor.
Yeah, thank you very much.
Okay, very good. Thank you all for asking questions. I think that, let me see, we have two on the chat room. Nice, nice presentation. Oh, yes. Okay, great. So I think that, okay, on the screen, Yuntao, can you make this a little bit larger? Okay. So I think that thank you all for attending today's talk, and thank you Dr. Azad Ghaffari, our speaker, speak about this 2 hours here answering questions. I hope that there are some interesting things some interest can sparkle from this, presentation. Next week, we will have Dr. Muhammad Mahdi. Oh, sorry, maybe I pronounce your last name. So that he will be giving a talk. We will shift the gear. So this is completely not on the vehicle side, but it's on the biomedical on this. So hopefully some of you can join us or share with your friends, and that anybody who you think might be interested in this imaging, biomechanics and etc. Can join us. With that, I think we will conclude today's presentation. Thank you all for coming. And then later on, we will put this on our website as well as our YouTube channel. Thank you.
Thank you.